Okay, so let's get started. So today we will wrap up the discussion on containers and container orchestration. So last time we started talking about Kubernetes. I'll finish those slides. And then for the rest of the class, we'll talk about cloud computing. Okay, so let's just do a quick recap. We talked about virtual machine migration. We talked about container migration and other container optimizations. And then I was talking about a system called Kubernetes, which is essentially a cluster management system that is basically using containers as its fundamental abstraction. And I mentioned that this is based on Google's Borg and Omega cluster schedulers. Okay, so Kubernetes has some abstractions that you need to know. I presented this notion of a pod last time. So essentially, a pod is an abstraction which contains one or more containers. And Kubernetes deals with resources and allocates resources to pods. Okay, so essentially, it takes pods and it puts them on machines and allocates machine resources to those pods. Okay, so it doesn't directly deal with containers. You assume that the containers are inside a pod, and then it essentially allocates pods. So you could just put one container in a pod, in which case the container and the pod are essentially very similar things, and you're still dealing with that container using the pod. But you could have more than one container in a pod as well. And how you decide what a pod is based on the application developer. Okay, when you design the application, you have to think about how to map the components of your applications to pods. The simplest approach is you take each component. Okay, let's say it's a database or it's a web server, okay, whatever the component of the web application is in this case, and put it inside its own pod. And then you allocate pods to machines, and you can also replicate pods. Okay, so you can have 3 copies of the web server running. That means there'll be 3 pods, each containing a container of that web server. Okay, so you can do these kinds of optimizations. And then at the end of the last class, I talked about this notion of a Kubernetes service. So what a service does is it takes pods and it exposes them to the outside world by first giving them a public IP address. Okay, so that users or browsers or any other type of clients can communicate with that application using the notion of a service that has been exposed by those collection of pods. This simple example here shows the blue boxes are essentially pods. The containers are in them. They're not shown here. So essentially, these 3 blue boxes are a replicated web server that exposed as a single service to the outside world. So then this entire service has a single IP address, and that service essentially performs load balancing and other functionality. Okay, so that's where we stopped last time. Then I'm going to continue from that point on. I should also mention a few other details. Okay, services are essentially durable entities in Kubernetes. By durable, what it means is if you create a service, Kubernetes will keep it around until you decide that you no longer need the service. Pods are a more temporary abstraction. They're ephemeral, which means that Kubernetes can say, I'm going to terminate this pod or I'm going to move this pod. So the mapping of pods to machines can vary over time. The number of pods it creates can vary over time. Okay? But service that the pod exposes will actually still be durable. It just gets mapped to the pods wherever they are, and that mapping might change over time. Okay, so now with those 2 abstractions in mind, the notion of a pod, which encapsulates containers, and the notion of a service, let's talk about the architecture of Kubernetes. Of course, so there are 2 things to keep in mind. There's an entity called the control plane. This is essentially the controller, okay, or essentially the entity that manages all of the machines in your cluster. Okay, so here's a picture of the control plane, but essentially it has 5 components. Okay, it has an API server, which is essentially exposing a REST interface, or essentially an programmatic interface that users or applications can use to communicate with the controller, saying, I need to start a new application, I need more resources. So all of these interactions with the Kubernetes control plane happen through the API server. Okay, so this is not the application API. This is the controller API. Okay, this is a management API. That's something you need to keep in mind. Okay, so the API server exposes a management interface. Okay, you can programmatically use that interface to make requests and so on. Okay, and then the state of what pods have been mapped to what machines, what applications are running, and so on, is kept at the controller, and it's kept in this entity called etcd. That's essentially a data store. Okay? Because the state has to be kept persisted, you keep that state on disk. So etcd is essentially a key value data store. Okay, it gives you certain properties, which is strongly consistent. It's highly durable. You can replicate that etcd component, which cannot read here. So that's etcd there. You can replicate onto multiple nodes for fault tolerance purposes, and it will keep them consistent using a technique called raft, which we are going to look at in maybe after spring break, a few lectures from now, which allows you to do consensus and so on. Okay, but for now, all you need to understand is the state of the cluster, okay, is kept by the controller, not in memory, because if the controller dies, that state disappears, but on disk, and that state is replicated. That's all you really need to know. Okay, and then you have three other entities. There's the controller manager, which is responsible for creating pods, replicating pods, and it monitors the health of pods. Is the pod running? Has it crashed, and so on? And has the node crashed? If any of failures are detected, it can restart the pod. Okay? So you can say, here's an application. It's in, I need a degree of replication of 4. That means that you need to run 4 copies of this application. It's going to now, you just say that, and Kubernetes decides which 4 machines are going to run your pods. If any of the pod crashes or the machine crashes, it will automatically reassign that pod or restart that pod without the application developer having to do anything. All of that comes as a service that Kubernetes will provide to you. Okay, so it ensures that failure recovery is built into the cluster management system. This is not something we had seen when we talked about other cluster scheduler. Okay. And then there is actually a entity called a scheduler, which is going to decide if you want to run 3 new copies of pods, which specific machine to pick. Okay. So we have looked at all kinds of schedulers before, least loaded. So you can say, pick the least loaded machine to run a container, or you can say, I need a machine with enough resources. It has to have enough memory, enough available cores to run that resources. The policy can be chosen flexibly. The scheduler supports ways by which you can decide how to do that assignment. But once you figure that out, it will implement that policy and map pods to machines. Okay? And then there is another entity here called the Cloud Controller Manager. This entity only comes into play if Kubernetes is actually running on a real cloud platform, as opposed to your own machines. So if you're running on a cloud platform, you have to interact with the cloud APIs to get machines and so on. And in this case, Kubernetes will use its cloud controller to interface with the cloud platform. Okay, and we'll look at some of those cloud platforms today, okay, in a little bit. Any questions on this? Okay, so this is the controller, or the control plane as it's known. Okay, the other entity in Kubernetes are the actual machines, okay, which we'll call nodes, okay, Kubernetes nodes. So here's a machine in the cluster. You may have thousands of these. Okay, they'll be running all kinds of pods and containers and so on. Okay. So each machine is going, in addition to actually running the application, containers, and the pods, it will have 3 other components that run on. One is called kubelet. Okay, so that's the Kubernetes agent that is running on every machine. And its goal is to ensure that the container is running, it's healthy. If it crashes, it will signal the control plane saying this pod has crashed. So do something about it. Okay, so it's basically monitoring the health of the container. Okay. Then there is something called a kubelet proxy that deals with the networking. As packets or requests come in for a particular pod, you have to essentially take those requests and hand it to the pod. Okay, because each pod is also going to have its own IP address and so on. So there is some network bridging that you have to do, because requests are going to come into the system and they have to be essentially sent to a particular pod depending on where the request came from and so on. So all of that networking and load balancing as well is done by the kubelet proxy. Okay. And the last component, but not the least one, is the actual container runtime. Okay? Because I said Kubernetes essentially deals with entities using container. You need some sort of a OS virtualization framework. Okay? And so that is essentially the container runtime. Now, Kubernetes does not require any particular runtime. It is designed to run with a whole set of these container runtime. So you can run with Docker if you want. You can essentially run with something called CRIO, which is yet another container framework. And there are a whole bunch of them. Okay, so it can run with any of those. Okay. So that's the end of the discussion on Kubernetes. I'm going to switch to cloud computing as a topic. There are questions. Is a good time. Yes, please. Yes. Right. So question is, pod is an abstraction. The entities that are running are actually containers. So what do we mean by pod has failed? So essentially a pod will fail if the container in it fails. And then container is also an abstraction. Remember, it's just a sandbox. What's actually running is the process. But at the end of the day, if the process that's running in the container, which is in the pod, crashes, then you restart. Okay. Okay, that's a good question. Question is, how do you decide when a pod fails if a pod has more than one container? If you have more than one container, any failure would mean that the pod health has been impaired and you have to do something about it, right? So you could, of course, try to restart that container. You don't have to just terminate the whole pod and move it somewhere. But in the default case, if there's only one container in a pod, then if the container fails, the entire pod fails. But you're right. You don't have to have only one container. You can have more than one. Okay. Yes, please. Okay, good question. The question is, does the container have a unique IP address or does the pod have a unique IP address? Okay, so if I go back 2 slides, okay, each pod is going to have its own IP address. Containers essentially only have processes. So you should just think of these processes as sandbox processes that run inside the pod, right? So pod will have a unique IP address. Okay. And each pod can communicate with any other pod using that IP address. And containers don't have their own IP address. So the container IP address is the pod's IP address. Okay. Yes, the question is, will the containers or rather processes inside the containers have to listen on different ports? That is indeed the case because the ports are essentially unique inside a pod. So if 2 containers are running the same service, you will have to run them on different ports, otherwise they'll conflict. Okay. Any other questions? Yes, please. Okay, question is, does this mean they share the same network namespace? A pod will have essentially one namespace. In fact, I think I mentioned that this is the wrong slide here. Right, so I think the first sentence there defines a pod. It says contains one or more containers that share the same volume and namespace. Right, so the containers themselves share the namespace. So they will not have their own namespace. They just have their resource isolated, but the namespace is shared because everything inside a pod can be seen by others. Right? Okay, question is, how is the resource isolated but they share namespace? Resource isolation simply means you can allocate memory and cores. It doesn't limit what you can see. Remember, namespace limits what you can see. Resource control limits what you can use. So containers can be given resources. Okay, resources in this case would be CPU, memory, and so on. But the namespace is not isolated at a container level, it's isolated at the pod level. That's a design decision. It's not that it's a right or a wrong decision. That's how it works. Okay, any other questions here before we move on? All right. So at some point, there will be another hands-on lab now, or not lab, actually, homework, maybe around after spring break, and you will play with Kubernetes, get a little feel for how all of these things work. Okay. But for now, we are going to switch gears to cloud computing. Okay, so there are 3 parts to the lecture, which we already did. Kubernetes a little bit out of order, so we're going to skip that. We're going to talk about data centers and cloud computing. Okay, so let's start with the data centers. Okay, so and then we'll use that to understand what cloud computing. So what is a data center? Okay, so essentially a data center is a large collection of servers and storage that provide these resources to application. Okay, so they're also referred to as server and storage farm. Typical data centers can vary in size. Okay, they may have many racks of servers, or they can have thousands and thousands of racks of servers. It depends on how large the data center is. So they can vary from small data centers to really large ones. But essentially, they provide computing and storage resources to application. And any organization that needs compute resources for server application will first build a data center. Okay, and then those data centers will have these racks of servers, and then you'll run your applications on those servers. Okay, so it's providing compute infrastructure. Okay, so they're used by enterprises to run server applications. They're of course used by all the companies that provide services that you know. Okay, so this would be Google, Facebook, social media companies, e-commerce sites, news organization. They all run their applications on large servers. These servers are sitting in some data center somewhere. Okay, those data centers could be owned by the company that provides the service, or those data centers could be owned by a cloud provider. Okay, so cloud computing platforms also use data centers. So you can just go to a cloud provider and run your application on their servers, or you can build your own data center and run your application on your servers. Okay, regardless, you can run all kinds of applications on a data center. And here is a picture. Actually, the picture is here. So here is a picture of one aisle of a data center. Okay, so each of these blue things is a rack of servers. So think of a rack. There are servers stacked in a rack, and then each rack will provide compute and storage infrastructure, and then there are lots and lots of these racks in a data center. So you can, this is one aisle, and you will have many such aisles. Okay, so you can think of a large warehouse-like room where essentially you have racks, rows and rows of compute servers. It's like a supermarket, except that you have servers on shelves instead of products. Okay, that's the picture you want to keep in mind. Okay, that's how a data center looks. Okay, so it's a giant warehouse filled with racks of servers, storage arrays. Of course, you need to put in a lot of cooling infrastructure, because all these servers are going to generate heat. Each server that runs is going to generate heat. So you need a cooling infrastructure to keep the servers cool. And you may need additional power infrastructure to ensure that if the power fails, there's a backup source of power or things of that sort, okay, to ensure reliability. Okay. So that's a picture you want to keep in mind, but let me come to what today's data center look like. Okay, so maybe 10 or 20 years ago, the way to build data centers was essentially more static. You went and you bought a large number of machines or servers from some company or a server vendor. You essentially put them on racks. You connected these servers to a network, and then you had lots of manual configuration to decide what application goes on what machine, what IP address to give it, and things of that sort. Okay, that's how so the traditional data centers were built. Okay. Now, most of these data centers have automated a lot of these tasks. Okay. So you assume that your application is actually going to run inside a virtual machine or a container. Okay. The mapping of containers or virtual machines to applications is done automatically by some controller. You don't need a system administrator to say, I'm going to run this application on this server. You can, but you would rather just tell the controller saying, here's an application VM or a container, go put it on some machine. Okay, so if it's Kubernetes, it will just put it in a pod and put it somewhere. If it's some other VM cloud controller or VM controller, it will do the same thing for its virtual machine. Okay, so a lot more flexibility. If machines get overloaded, you are going to live migrate your virtual machine to some other server. Okay, so all of the techniques that we've been talking about, live migration and scheduling, all of these are built into the controller framework that manage these data centers. Okay, so that's what you want to keep in mind. A lot of automation has been put in so that you can manage this very large infrastructure in an easy way. without having to do a lot of manual work. Any questions so far? Okay, so this is virtualization. We already looked at this. Okay, so here's a rack of servers. Okay, we assume that each server is going to run a hypervisor. Okay, that's that blue thing that you see on top of that server. And then that server can run multiple virtual machines or containers. Here you see virtual machines. Each virtual machine will run an OS and applications. Okay, and this is going to be the case for every server in the rack and all the racks you have. Okay, and you can actually virtualize desktops as well. Okay, you can essentially get a lightweight machine and run your actual computations in the cloud, where you can just use a remote application to essentially access your desktop. So you can even now put desktops in the cloud rather than putting server applications. Okay, so several companies have started doing that as well. Okay, if you do that, then your machines are called thin clients. Okay, you will hear the word thin client, that essentially, as opposed to a fat client. A fat client means you have enough CPU, memory, and disk to run your applications locally on your machine. Okay. A thin client essentially says that the application, in this case, they are desktop applications. They are running remotely, and you are simply connecting over some graphical interface to a remote machine and doing computation with a relatively low-end device. Okay. So virtual desktops are essentially a thin client technology. Okay. You are using virtualization to take whatever is on your PC and run it in the cloud. You can just connect to that machine and do whatever you need to do. Okay, so we already know enough about virtualization from our previous lecture, so I'm not going to go into too much details here. But the thing you want to keep in mind is our hypervisors are going to allow us to take each server, and we'll think of them as capable servers. There'll be lots of cores, lots of memory, lots of disk. So you don't want to necessarily run only one application if it doesn't need all of those resources. If an application needs only a subset of the resources on the machine, you construct a virtual machine. Okay, you allocate a subset of the server resources, put the application in that VM. Okay, and then the rest of your server resources can be allocated to other VMs. Okay, so essentially, you're slicing your physical server into virtual servers, okay, and then allocating virtual servers to applications. Okay, and we know that each VM will run its own OS and applications. If it's a container, you only run the application. Okay. Now you can do all kinds of optimizations when you do this. Okay, if your VM needs more memory, okay, you can just resize the VM. Just as we live migrated the VM, you can simply allocate more RAM to the VM. You can allocate more disk to the VM. Okay, you can allocate more CPU to the VM. You can do this while the VM is running. Okay. Normally, you can't take a physical machine and just allocate more memory. Okay, you literally have to shut it down and insert more memory into it. Okay, in this case, you can just take some physical memory on that server and assign it to the VM. Okay, so you can rapidly adjust the allocations done to the VM while the application is running. You can, of course, live migrate the VM if you need more resources than are available. So the use of virtual machines gives a lot of flexibility, okay, that you would not have if you're running your applications on physical servers. Okay, this is why all data centers and cloud platforms essentially use the virtualization architecture. Okay, virtualization is the building block for both cloud computing and modern data centers. Is that clear? Okay. Yes, please. Okay, question is, the term virtual private server, does it refer to virtualization, right? So virtual private servers are essentially a VM or a container that's given to you that looks like a real server. Okay, so it's a virtual server. The word private simply means that you have access to it and no one else has access to it. Okay. All right. So ignore the, so here it shows an animation where VM1 needs more resources. So you can live migrate VM2 and resize that VM. Okay, but you leave that aside for now. Okay. Now, I want to introduce one term that you should know when you talk about data centers, and that term is called power usage effectiveness, or PUE is the acronym. Okay. So you will often hear this data center is very efficient, it has a low PUE. Okay. So it's good to understand what that actually means. Okay. So first thing is you want to understand what are the costs of running a data center. Okay, so here's a pie chart. Okay, so what you see is the red is essentially and red and green actually. It's essentially power and cooling. Yes, cooling also takes power. Okay, one is power to run the server, the other is power to cool the server. Okay, and the rest of it is all other costs that you will pay to run your data center. So you will see that almost half of the cost of running your data center comes from electricity costs, because it takes a lot of electricity to run lots of these servers. It takes even more electricity to get air conditioners to cool those servers. Okay? So a large portion of operating your data center is actually energy or power cost, essentially electricity bill cost. Okay? So not surprisingly, there is a lot of work that has gone into how to reduce the power footprint of your data center. Because if you reduce the power consumption, you are going to get more efficient more efficient data center that's going to have lower operational cost. Okay? And PU is a metric that captures how efficient your data center is. Okay? And the way you, the ratio or how you compute PUE is essentially shown there. It's the ratio of the IT power over total power. Okay? Put another way, is the electricity consumed by servers divided by the total electricity that your data center needs. So in the denominator, you have the server electricity, air conditioning, cooling electricity, plus if you have network switches and all these other things. Right? So it's server power consumption or total power consumption. Okay? Now, since our applications are actually running on servers, what we care about is actually the server power consumption. Okay? So all the extra is overhead. Cooling is overhead. It doesn't actually contribute to applications doing any better. You just need to have cooling so the servers don't melt when the temperature goes up, right? So the ideal PUE is 1, okay, where you only use you only use electricity to power the servers, and all the extra electricity you need is 0. Okay, but you cannot actually get 1 in practice. So all you can do is come very close to 1. Okay? So the most efficient data centers have PUE that start approaching 1. Okay? Now, 10 years ago, if you took a standard data center and say, what is its PUE, you would get a number that's almost close to 2. That means for every 1 unit of electricity you put in your server, you're spending another unit for everything else, like to power your air conditioners and power your network switches and routers and things of that sort. Okay? So that means your overhead is almost twice in some sense. Okay? Now, over time, all of those extra costs have been optimized. Better air conditioning has been put in place. In many cases, you don't use air conditioning, you use outside air. If it's cooler, you'll basically just take your hot air from the servers and just vent it out and just get ambient air. So you don't use air conditioning unless it's very hot. So all kinds of cooling optimizations have been done. What that has resulted in is PUEs have come close to 1 for the most efficient data centers you can build. And many of them are built by companies, Google and Facebook and Amazon. They tried because their data center costs are so high. Even a small reduction in PUE saves them millions of dollars of electricity bills. Okay? So reducing the PUE has been a big area of research in data centers for a number of years. And now we are getting close to 1 already. If you're 1.1 or 1.05, it's not a whole lot of room left. You're already close to where you are. But if you have an inefficient data center, it has a PUE of maybe 1.8 to 2, then there is still room to optimize it. And there are still some old ones that are not very efficient. Okay? So this is a metric you want to keep in mind. When you talk about data center efficiency, the way you measure that efficiency is through this metric called power usage effectiveness. It tells you the overhead of how energy costs in terms of how much you take to power servers with respect to how much is the total energy consumption of your data center. Any questions on this? Okay, so we'll move on. And so with that background of what is a data center, how do you make it efficient and so on, now we have enough to talk about cloud computing. Okay. So first of all, what does cloud computing mean? You probably all heard the term, at least if not used cloud servers and cloud platforms, but let's try to define this term. Okay. So very simply put, cloud computing means you use remote servers to run distributed applications. Okay. The servers are somewhere remote and they're running some sort of distributed, in most cases, they're client server applications. The server part is running on those remote servers. The client part is running somewhere else. Okay, there's a more detailed definition than that, but for our purposes, that's good enough. Okay. Now, a cloud platform provides that kind of service to us. Okay. So essentially, a cloud platform will be a data center, okay, which will have these remote servers. Okay. And you will run applications on those remote servers. Okay, now the other thing you want to keep in mind when you talk about cloud computing is the owner of the servers is different from the owner of the applications. Okay. If you, as an organization, buy your own servers and you run your own applications or deploy your application on the server, the entity that owns the machines and the entity that owns the application are one and the same. Okay. It's like you have a laptop, you own the laptop. You bought some application or you downloaded some application, you ran it, so they're your application. So your applications run on your machines. Okay. In the cloud, that is decoupled. Okay. The cloud provider or the cloud platforms owns the servers. The applications are owned by third parties, and they are simply leasing or renting server resources to run their applications. Okay. So essentially, a cloud computing platform is a data center where remote resources can be leased by any user or company to run their applications. So you don't have to buy your own servers. You can just go rent a server. Okay. And moreover, you can pay for those servers by the hour or by the minute. So if you only use that server for 3 hours, you pay for 3 hours of server time. Okay. As opposed to trying to buy a server, then you're stuck with that server. Right. So there is no need for organizations now to build their own data centers or IT infrastructure. They can simply lease these resources. Okay. So cloud computing has changed the model from buying resources to leasing resources. Okay. And that gives you quite a bit of flexibility, okay, which are all mentioned here. Okay. So first thing is your servers are remotely accessible, so they're available from anywhere over the internet. Okay. That would be true for other servers as well, and that's true for the cloud. Okay, but importantly, the billing model for the cloud is what is called pay as you go. Okay. So you can get however many servers you want. You can use them for as long as you want, 1 hour, 10 minutes, 10 days, 10 years, and you will get a monthly bill that says for this month you use these many servers, and for each server is used for this much time, and you will get billed accordingly. Okay, next month your usage can be different from the previous month. So you can flexibly change how many resources you need as your needs change. Okay. If you had to buy your own servers and now you need 5 more servers, you got to place an order, have the servers come to you, deploy them, install applications, and so on. Here, if you want to get 10 more servers, you just make a request to the cloud providers, and a few minutes later, they allocate you that server. Okay. So the time to provision machines has shrunk to minutes from weeks. Okay. So it's much more agile in terms of how you can deploy applications and change their resource allocation. Okay. And you can pay as you go. Okay. Okay. So related to that is it's highly scalable. You can obtain resources on demand. Whenever you want machines, you can acquire them. When you're done with them, you release them. You only pay for the time you use those machines. Okay. So that's much more flexible from an application developer or a company's perspective. Okay. And you get economies of scale because the cloud provider hasn't built these machines just for one customer. Okay, they built a very large data center, so it can service hundreds of customers. So you get efficiencies of scale as you make things bigger, and you get individual customers of the cloud are going to get the benefits passed on to them because that server is going to be cheaper than if you build a small data center yourself, where you don't get these economies of scale. Okay. So all kinds of benefits from using cloud computing. Okay, before we go into details, are there any questions about the definition?
Okay, so there is a question here that asks about PUE.
Okay.
So the question says, how can PUE be greater than 1? Because PUE is equal IT power
Okay, I think that was flipped.
Yes.
It should be total power or IT power. So PUE is always going to be greater than 1 because the denominator, I think there's a typo there. The denominator should be IT power, then the numerator is total power. So I'll fix that on the slide. Thanks for the clarification there, question. Okay, good catch. All right, so coming to cloud stack. So there are different kinds of cloud platform. Okay, cloud, when you say cloud, it doesn't come in one flavor. It comes in many different flavors. Okay, and here are 3 different flavors of what kinds of cloud resources you can get. Okay, the lowest layer is called infrastructure as a service, or IaaS. So that's the acronym. Okay, and then you have something called platform as a service, or PaaS. And the top one is called software as a service, or SaaS. Okay, and so what is the difference between all of these things? Okay? So what changes is, as you are in the lower levels of the stack, you get bare bone hardware resources, and then you have to run the deploy your operating system, run the software, and do whatever you need to do. Okay, so as an infrastructure level, you can just acquire machines, and then you own those machines for as long as you keep them. And then you have to run your own OS, you can run your own application. So it's just like going and buying bare bone machines and doing whatever you need to do. Okay, that's called infrastructure as a service. So you get servers and you get storage. Okay, now if you get cloud service at the platform level, then what you do is you no longer get individual servers. You essentially get resources where you say, here is my application. You just give maybe some code or a container. And then the platform will decide how many servers to put it on, how large the server should be, and so on. And you are now charged based on some other metrics, such as how many requests are being serviced by your application, rather than how many servers you want to use for your application. Okay, so now as a developer, you don't need to worry about, should I get a small server for my application? Should I get a big server? Should I get 2 servers? Should I get 5 servers? Because you have to think, if you're going to get resources at an infrastructure level, how many machines you need. You may not know, because you need to figure out how popular your application is going to be, what kind of workload it needs to service, and then decide how many machines to get. But if you make an incorrect estimate, then you may have an overload, or you may end up paying more and your servers are not used. Okay, so that may not be the most effective way to acquire resources. But if you deploy your application on the platform rather than on individual servers, it's the cloud provider's job to decide all that. They will decide how to scale your application, how many servers to run it on. As the workload changes, they can figure out to allocate more resources. All you are doing is you're paying for the workload. You're not paying for servers. You're paying for how much requests were serviced by your application. Okay? So it simplifies how to deploy your application on the cloud from a developer's perspective. You don't need to worry about things like servers. You just worry about writing your application and deploy it on a cloud platform. Okay? So this is called a platform as a service cloud. Okay? The very top is software as a service cloud. So in this case, you don't even worry about writing the application. Somebody wrote the application and deployed it in the cloud. You basically go get an account on that application and then you do your thing. Okay? So things like Gmail and Google Docs and Google Drive, those are all software as a service cloud services. Right? Because the mail server is already deployed for you by Google. Okay? You are just getting an account on that mail server and doing your work, sending email and so on. You neither have to get machines, nor do you have to write your code for the mail server and deploy it. So all of the work is done. You're just getting the service. Okay? So that's called software as a service. Okay? So you have these 3 layers of cloud platforms. I'm going to talk about the first 2 in a little more detail. Okay, infrastructure clouds and platform clouds. Any questions about this? Okay, so let's talk about infrastructure as a service. I'm going to use Amazon's Elastic Computing Cloud, or called EC2 Cloud, as an example. But pretty much all cloud providers have similar abstraction. Okay, there are many commercial cloud providers. Microsoft has Azure, Google has Google Cloud, Amazon has EC2, and then there are dozens of smaller cloud providers. Okay? But when they offer their service in terms of infrastructure as a service, you essentially are going to rent servers and storage. You are going to say, I need a single core machine. Okay? Or you will say, I need a disk with 100 GB of storage space. Okay? So you are essentially going to get resources in that granularity, and then you use it however you want. Okay? So you're renting servers and storage. In this case, the platform will rent it to customers. And what the customer is getting is essentially virtualized services. When you say, I want a 2-core machine, you don't get a 2-core physical machine. You get a virtual machine that has 2 cores allocated to it. Okay? And the same is true of disk. If you're getting a disk, the disk is essentially virtualized. And you essentially pay by the hour. Now you actually pay by the minute. All cloud providers have gone to per minute billing model, but the hourly cost is not much. If you get a small server, you might pay something like 2 cents an hour. Okay? So it just comes to a few dollars a month for a tiny machine. But if you take a large machine, that may cost you $2 or $3 an hour. Okay? You can get machines with GPUs, for example. They tend to be very expensive. You may pay tens of dollars sometimes if you want to get a large one. So if you get it for a long time, you're going to get a large bill because it's a more capable machine. Okay, so, but what the cloud provider allows you to do is it gives you machines of different sizes. Okay, you can say, and these sizes have labels. So you can say small, medium, large. Okay, then there's extra large and 2 extra large. So there are all kinds of names that indicate the size of the machine. The size is pre-configured. You can't say, I want 3.5 cores or something like that. You have to pick one of the configurations they provide, and there's a charge associated with it. Okay? Same is true of storage. There's a charge associated to storage. You just decide how much storage space you need. Okay? So that is infrastructure as a service cloud. So here you are going to get a bare bone machine. Okay? You can specify that it needs to run Linux, or you can specify the OS. In many cases, there are pre-built images, just as you had container images. The pre-built images, you can say, I want a machine pre-configured with Ubuntu. It should run Apache web server, and it should have MySQL database. You can get an image that's already built by someone. They will get, essentially, when the machine comes up, the software is already on there because you got the right image. But you could just say, I just need an Ubuntu machine. I'll do all the work myself. And they'll just give you OS on the bare bones OS on the machine. Then you get access to the machine, you deploy your applications and configure it. Okay? So that is infrastructure as a service. And in addition to different sizes of servers, there are different kinds of billing models depending on what the server gives you. Okay? What kind of abstraction the server gives you. The simplest type of machine is what is called an on-demand instance. An on-demand instance, as the name suggests, you acquire it on demand. You can ask for a machine anytime. Okay, there is no commitment of how long you need to hold it. Okay, you can say you use it for 10 minutes and you terminate it, you will get billed for 10 minutes. Okay, so the customer can ask for the machine at any time. They can give up the machine at any time. They are just billed for the time for which they held the machine. Okay, it's purely on demand. Okay, so you can provision it on the fly, pay by the minute or the hour, and you get to keep the machine until you terminate it. Okay, that's the simplest mod. And you can say, I want a small on-demand machine or a medium on-demand machine. All the sizes can get assigned to what type of machine it is. In this case, it's on-demand. Okay? But there are many other models also. Okay, there's something called a reserved instance. So in a reserved instance, you ask for a machine, but you commit to holding it for a long period of time. Typically, you can say, I need a machine for 1 year. Or I need a machine for 3 years. I commit to actually keeping it for 3 years. So if you make that kind of a commitment, okay, the cloud provider will give you a much lower rate than on demand, because you are already committing to a contract saying, I will hold it for a long period of time. So you can get it at a discount. The same machine configuration, you get a lower price because you are just committing to holding it for a longer period of time. Okay, that's called a reserved instance. Okay, or also longer term instance. Okay, and then you have these other instances called spot instances. Okay, so what is spot instance? Essentially, the cloud provider at any time will have unused capacity on their cloud platform because they have built their cloud for the peak load. most of the time you have an average load, so there is still unused capacity in your data center. Okay, and they're not making any money when there is servers are not getting used. Okay, they only get paid when some customer actually uses their machine. Okay. So what many of them do is they take this excess capacity and they sell it at a high discount using something called a spot server. Okay. So you basically can say, I need a spot server, and you'll get a 90% discount on the same server over an on-demand server, because this is just unused capacity sitting there. So they're giving it to you for a much lower price. Okay. But it comes with one caveat, because then you would say, why would I not just ask for a spot server? Why do I want to ask for an on-demand server? Okay. The main difference for the spot server is it can be revoked. It can be taken away from you. Because if a customer comes and says, I need on-demand servers, and you've given all your excess capacity as spot servers, you can actually go and reclaim your spot server from the customer. So you can give them a warning saying, I have 2 minutes before I take the server away, save your work, and then the machine will be shut down and taken away. Okay. So spot servers are given at a high discount, but they can be reclaimed when the demand for cloud resources comes back. Okay. On-demand servers and reserved servers are non-revocable. The cloud provider cannot take them back, okay, because they're billing you for it. You get to keep it for as long as you want as a customer. Spot servers are given at a much higher discount, but because it's excess capacity, but it can be revoked. Okay. Now, spot instances tend to be a cheap way to run large computations at off-peak periods. Okay, you can get 1,000 machines in the night when there is lots of excess capacity, run some computation, do it on the very cheap. But if you did the same thing on on-demand server, your bill will be maybe 10 times bigger. Okay, but you have to be willing to have some of those servers taken away at short notice. Okay, so that's a risk you are going to have, but so long as you are willing to pay that, take that risk, that's a much cheaper way of doing computation. Okay, needless to say, you are never going to run web applications on spot servers. Okay, I assume that's clear why. Sorry, what did you say?
Availability.
Okay, availability. You don't want your web server to go down because the spot server has been taken away. Right? So web applications, which should be always run on on-demand reserved instances if you want to keep them up. Okay, so what will you run on your spot servers if you don't want to run web applications? Okay, so you'll run bad jobs, where if the job fails, okay, that's fine. You can always restart it. It's not that the user is sitting there trying to connect to your online store and the store is down or something like that. Okay? So the use case for spot instances, batch application, large data processing, you can do MapReduce, Spark, all of these things you can run. But you don't want to run web applications, because that's a problem. Okay. All right. So next is platform. Yes, you have a question. Okay. Question is, how do you preserve the state if the bad job is terminated? So I mean, that's a more general question about if the spot instance is taken away, how do you save the state? Right? So there are two answers to that question. If you are running on spot instances, you have to have built in some way to save your state. So either you say, I periodically take the work and write it to disk. Okay? So every hour I write it to disk. So at most you lose 1 hour of work because I just restart from the previous saved state. Okay, so you have to write your application that way. If you just run some random application and the spot server is revoked, you lose all your work. So you have to restart. Okay? So you will have to essentially add a little bit of extra work to do that. So if you are running MapReduce or Spark, for example, it has a function called checkpoint, right? So every 1 hour in your code, you just call checkpoint and then you save. And if you have to restart Spark, you just start from the checkpoint and you're fine. Right? So that's what you will have to do. You have to change the application a little bit. Yes, question. So are you referring to cloud provider or application? No. Right. So question is, at off-peak period, how should the cloud provider manage its server? Right? Can you turn off some servers to save electricity. In fact, many cloud providers will actually do that because there's no point running 1,000 servers when they're sitting there idling, because they're consuming electricity and you pay for electricity, right? So most of the time, what you will do is you will either rent those unused servers as spot servers, and if somebody rented them, you're still getting some revenues from those servers. But if nobody is renting them, you can put them in some sort of a low power mode where they can be rapidly restarted, but you're not consuming electricity, right? So you can make those optimizations. Other questions? Okay. Okay, so next is platform as a service cloud, where now you're providing a different level of abstraction. Rather than exposing bare servers, not bare servers, rather virtual machines as servers and virtualized storage, you are going to expose a platform. Okay? So what application developers do is they will essentially provide code to that platform. They'll say, here is my code. I wrote it in Java, so here is my Java application, or I wrote it in Python, or I wrote it in many different languages that can be supported. Right? You can write it in Node.js or .NET, whatever language is supported by the platform. You can write your application and say, here is my application, run it, and bill me by, instead of hours of server time, bill me by the number of requests serviced. Okay? So now it's the cloud provider's job to decide how large a VM to put it in or how many machines to replicate it on. All of that is now going to be done for you by the cloud provider. You are just writing your code and you're making the code available by executing it on the PaaS platform. Okay? So users, or in this case, it should be developers, not the end user, don't need to provision or manage server resources. You are now billed based on your workload as opposed to server usages, things like requests served and bandwidth usage and things of that sort. Okay, so essentially this is going to simplify the usage of cloud for many developers. You don't need to worry about, if you're not using something, you don't need to pay for it, because if you get cloud servers, you don't use it, you still pay for it unless you give it back. Okay, here that's not the case. Okay, and in a few weeks time we'll talk about something called serverless computing. It's a new kind of cloud model which is very similar to the platform as a service model, where serverless computing doesn't mean there is no server. That name is a little bit misleading. It simply means that as a developer, you don't actually have to get servers to run your application. You just write code and give it to the cloud provider, and they deal with all the servers, allocation, and so on. Okay, so that's a very similar model. We'll talk about that at a later time, but I just wanted to make that distinction clear here, or similarity clear here. Okay, so now let me introduce a few other terms that you should know when you're talking about cloud computing, which is public cloud, private cloud, and hybrid cloud. So the cloud platform that we've been discussing so far is called a public cloud. A public cloud is, as the name suggests, is an internet-facing cloud. Its servers are accessible over the internet, and it's available to anyone who's willing to pay the cloud provider for an account and get servers. This is called a public cloud. Okay. Now, many cloud providers will also build smaller versions of their cloud platform that are dedicated to a single company. If you're a large organization, you say, why don't you build a cloud for me? Okay. And so what the cloud provider will do is they will take some of their racks and they will essentially run cloud service and make it dedicated for one organization. Okay. So those cloud machines are now dedicated to a single organization, and employees of that organization can still go and request machines, except that they'll come from their private pool, not the public pool. Okay. So this is called a private cloud. If you dedicate some part of your cloud to a single company, or you can dedicate an entire data center as well. If it's a large organization, you can build an entire data center for that organization. But now your employees or users are essentially acquiring machines in a cloud-like fashion. You don't need IT administrator to say, do you want a machine? I'll give you this one, go run your application. You still do the same thing you did for a public cloud. You say, give me a virtual machine. Okay, I need a small size virtual machine. So you are using the cloud model to allocate resources on your servers. The cloud provider is essentially running those machines for you. Okay, so you're essentially getting a large number of machines and it's offering a cloud-like service to your employees. Okay, this is called a private cloud. Okay, you can, of course, as an organization, run your own private cloud. You can essentially get some cloud management software, buy machines, and run the cloud software. Okay, so for example, if you ran Kubernetes on your servers, you essentially get a private cloud of containers. Because that Kubernetes is giving you cloud-like service. You can just allocate a pod and the pod gets placed automatically. All of that comes to you. Okay? So in either case, regardless of whether the servers are owned by the entity or a cloud provider, this is a cloud that's dedicated to a single entity. Okay? It's called a private cloud. And then you have something called a hybrid cloud. Okay? As the name hybrid cloud would suggest, it combines a private cloud with a public cloud. Okay, so that's why it's called a hybrid cloud. So you might say, why would you do this? What benefit do you have by taking some machines from a private cloud and some machines from a public cloud? Price. Can you explain a little more?
For example, generally the public clouds are cheaper and private clouds are lower. If I want to some workload to public cloud, then I will save money.
Okay, so you're saying if public cloud is cheaper, so I can move some workload to public cloud and save money. That's true, but if public cloud is cheaper, you should not have a private cloud to begin with. Right? You should put everything there. Yes, please. Okay, can you explain a little more? Right. Okay. Right. Yeah. So the reason you want to even think of something like a hybrid combination of private and public is because your workload is going to vary over time. The workload is dynamic. Workload is not static. Okay? It will have all kinds of variations. Many of these are called time of day variations, higher during the day, lower during the night. There will be seasonal variation at certain times of the year. The workload is higher than other times and so on. Okay? So if you are running a private cloud, you may start running out of capacity on that private cloud because all of your servers are getting used. Okay? Now, if some employees comes and says, I need 10 machines, you say, I don't have 10 machines anymore. Okay, come back after a month. That's not a good thing to tell them. Right? So what you can do in that case is if you run out of capacity in the private cloud, you can essentially get that extra capacity you need temporarily from a public cloud. Okay? And then allocate it. And once your demand reduces, you can release those machines and go back to using your private cloud. So in some sense, your public cloud is like an overflow. Okay? If you run out of space here, you overflow into a public cloud. Okay? This is also called cloud bursting, where you are bursting from a private cloud to a public cloud whenever you run out of capacity locally. Okay? So this is a typical use case for a hybrid cloud, where if you have dynamically varying workloads and you are approaching peak workloads and you don't have enough resources locally, you get those resources from another cloud. In this case, it's a public cloud. And then you get a hybrid. Okay? So many cloud providers will also do that. They will run a private cloud. If you need more capacity, they will allocate capacity from their public cloud, and then they'll deallocate it when the demand goes away and so on. Is that clear? Okay. So one last thing, and then I think we're kind of done, maybe 2 slides. So cloud workloads, I already mentioned lots of these already. So typically you use cloud servers to run web applications, client server applications, so on. We talked about running batch jobs on these cloud machines. Data processing and analytics is another big class of workloads. You have a large data set, you put it on the cloud, you rent some machines, you process it, and you deallocate the machines and you're done, right? So it's a cheaper way than saying I go and buy a bunch of machines, but I use them only once in a while. Okay, so data processing, analytic workloads run on the cloud. Okay, the newest emerging class is to run AI workloads, mostly machine learning training. Because if you have very large data sets, you want to train them, you can train them on cloud servers. Okay. Many cloud servers now give you what are called GPU instances. So these are servers with GPUs in them. So you can use GPUs to accelerate your training and so on. Okay. So different kinds of workloads that you can run on your cloud. There are more and more high performance computing workloads that also run on the cloud. Okay. Traditionally, these workloads have been run on supercomputing machines. Okay. And supercomputing machines often have dedicated hardware that is optimized for parallel applications or high performance applications. But increasingly, cloud providers also give you specialized instances that are designed for certain class of workload. So in many cases, it's cheaper to rent cloud resources than get a supercomputing cluster, because that's going to be extremely expensive. So many HPC workloads are migrating slowly to the cloud as well. There are quite a few of them still run on dedicated supercomputers. Yeah, but increasingly, it is becoming economically, if cost effective, to run them in the cloud. Okay, so variety of different kinds of workloads that you can run. So there are different kinds of models you can use and so on to run them. Okay, so there's also something I wanted to say about cloud storage, because all of our discussion has been on cloud servers. Okay. So same concepts apply, just as you can get at an infrastructure level server resources from the cloud, you can also get storage resources. Okay. And the cloud actually providers will give you different types of storage resources depending on your need. Okay. You can get something called object storage. So this is a large blob of storage where you are going to use something called get and put operations to put large amounts of data and retrieve large amounts of data. Okay. So this is a different kind of storage than you may have encountered, because most of the time on our local machines, we have disk storage and you have a file system. So you store data in terms of files, you organize files in terms of folders. So typically you use file systems and files to organize your data. Okay. But there are also other ways to organize your data, and one of them is called object-based storage, where instead of files, you have something called objects. Objects could include anything. It could be a collection of files. It could be a large data set. It could be a large file. And you can essentially read or write entire objects into object storage. So cloud providers actually give you object storage as the one type of storage you can rent from them. And you can get lots of storage and put objects in them or retrieve objects. Okay. You can also get traditional block storage, which means just disks, and run a file system on it. Okay. So when you get a machine on the cloud, you can also say, I want a disk of a certain size, and you can then run a file system and put regular files on it. Okay. So that is called block storage. Okay. In that case, the disk is attached to that machine, and only that machine can access that storage. Okay. You can also get network storage, okay, which is essentially a network file system, and multiple machines can then access that storage. So this is local disk, this is network disk. So you can get both kinds of disks from the cloud provider. Okay. And you can also get something called archival storage. Archival storage, as the name suggests, is meant to keep data backups that you are not going to access all the time. So this is typically put on cheaper disks or slower disks. So you get them for less price than maybe a block storage, okay, which is designed for high performance. This is designed for storing large amounts of data, but not necessarily high performance. So you use that to keep your data backups and things of that. Okay. So these are cloud models that a cloud platform will provide. Okay, but there are other cloud models that you're probably aware of also that are just from dedicated cloud storage providers. Okay, Dropbox is a good example of a cloud storage. Okay. Dropbox doesn't give you machines, it only gives you space. Okay. And in Dropbox case, what it does is it essentially has a cloud server that synchronizes your machines and files on that machine. Right. So you put some file onto your Dropbox folder on one machine, it gets uploaded to the cloud, and then it gets synchronized across all of your machines that is running Dropbox. So this is another way of using cloud storage where you're synchronizing storage across multiple machines. Okay. And then there are other kinds of storage that you're familiar with, like Google Drive, OneDrive, Box, and so on, that essentially give you a cloud disk where you just keep files on that disk and you can access from any machine. So these are more specialized cloud storage providers as opposed to general purpose providers that are providing storage that go with machines that you get on that cloud provider. Here you are just getting storage. Okay? And then you can get cloud backups where you can just back up a machine to the cloud. You can get cloud media storage. You can get photo storage to keep all your photos that you take on your smartphone in the cloud. So there are all kinds of other storage models for the cloud as well that are for more specialized needs as opposed to general purpose needs. Okay. I think one last slide and then we are going to end. So this is essentially cloud orchestration, and I won't spend too much time here. All I wanted to say is the component of the cloud that I did not talk about is the cloud controller, okay? Because the cloud provider of the cloud platform is still going to have to manage all of its machine. So it will have a control plane. When your customers ask for machines, you make that request to the control plane. The control plane will automatically allocate those machines and so on. Okay, so conceptually, the cloud controller is no different from the Kubernetes controller that I spoke about earlier, but that's also managing a cluster and container. The cloud will also have a similar controller, except that's managing virtual machines, not containers. Okay? So your customer can request instances. The cloud controller will spin up or create new virtual machines on. It will decide what servers to run it on. It will configure the networking storage. It will boot the VMs. All of that is automatically handled by the cloud controller. Okay? But the important thing to keep in mind is all of these tasks are referred to as cloud orchestration. So when you hear the term orchestration, you should think about managing all my cloud resources and allocating resources to application. Okay? How to automate that, that is referred to as cloud orchestration. We already saw how to do that very briefly in the context of Kubernetes. Okay? Cloud platforms are not going to be any different. They have to do the same thing. Okay, so I'm going to stop here. If you have questions, you can ask. Or if there are any questions, are there questions on Piazza? No. Okay. All right. So are there, before we stop, since we have 5 minutes left, are there any questions about the lab that you want to ask that I can answer and everyone can benefit from that? Yes.
There is a big queue set, request queue set. Let's say the queue is built and additional requests are made. Are we expected to change that?
Okay. Question is, in the first part of the lab, if you use the bounded size on the queue and the queue is full and additional request comes, what should happen? Should you drop those requests or not? Okay, so ideally you can just wait, because the producer thread is going to just wait to put that request in the queue, and all incoming requests will block at the socket level. So you don't really need to do anything. The OS and the synchronization will take care of it for you. You can drop requests, but this is not required in the lab. Okay, so that's something you can do as a more advanced feature, but it's not really required. If the queue is full, you just wait until one slot becomes available, and then you put that request, and then if it fills up again, you wait. That's all that you are expected to do. Much simpler. Okay, you don't need to do anything more advanced right now. Okay, anything else? Your question? The question is, if the queue is full and the main thread in the server is blocked trying to insert a request in the queue, and the queue is full, so you will not get the lock, you will block, what will happen to all the incoming connections from other clients? Right? Typically, when you make a connection and the OS accepts it, there's a long time before it times out. So you essentially, your request from the clients will come and sit in the OS buffer, waiting for the server thread to pull them out. Okay? If you send lots of requests, the OS buffer will fill and the TCP will give you error at the socket level. But I don't think you are injecting a load high enough to even hit that capacity. So what will happen in this case is, if you have a small bounded buffer and you fill it up, okay, requests will start getting queued at the OS because your server thread is blocked, is not even taking connection. But as it frees up, it will pull connections, requests from the OS buffers, accept the sockets and proceed. Okay. Yes, it will get queued in the buffer. You don't need to worry about it. All this is automatically happening. Okay, so that is why you don't need to drop requests or anything. They will just sit somewhere and then they will get processed after a while. Okay, yes.
So then the main thread should wait for the
Yeah, if the main thread, if it's blocked, it should wait for a notification from the consumer saying now there is, I've pulled a request from the queue, so you can insert. So that's standard producer consumer. That should happen in a typical producer consumer implementation. Okay. All right. Anything else? Okay, so there are extra office hours we have announced on Piazza. There's one right after this class. The TA will be waiting. So if you need answer questions, go talk to it. Okay. So if there are nothing else, we'll